Good afternoon. Can everybody hear me and see the transparency?
Yes.
Are there any questions?
I have a question about exercise set 3.
Okay.
Could you explain to us how we would go about creating a Turing machine like the one in question 4b?
Hold on. 4B. Okay, so this is a Turing machine in which the number of zeros is equal to the square of the number of ones. Let's see, what was it? Zero to the I, 1 to the j I is equal to j squared. Okay, so what is the idea here? You're basically looking at a tape, and you have a bunch of zeros, and then you have a bunch of ones. Okay. So what does that mean? That means that you basically have to mark off how many zeros for each one. You have to mark off as many ones as you see. For the zeros. And then you have to do that again for every one. So how can you go about that? Well, obviously, as with Turing machines, there are many, many different ways. Let's do the slow way. Okay, so we have the zeros, they're still there. Then we have the ones. And then what we're going to make is a copy of the ones and call them twos, just to keep things separately. So whatever ones we have, we're making, for every one we see, we make a 2. So we know how to do that. Let's ignore the zeros for the moment. So the idea here is that for every one that we find, we're going to write a 2. So we can do that by simply going to the end. We mark the 1, say this is a 1 prime, and we generate a 2. Replace the first blank with a 2, and then we go back the usual trick until we hit the 1 prime, and then we go to the right of it, and if this is a 1, we prime it, and then we move over here and make a 2, and so on and so forth, and we keep on doing that until we have basically primed every one and written a 2 for each of them. Okay, so at this point, we have the same number of ones as we have twos. And now what we're going to do is we'll go back, and of course there is a little bit of a problem because we really should have marked the zero, the first zero, so we know where the beginning is. So let me just put a bar on top of that zero, which we're going to treat exactly like a zero. And then what we're going to do is we mark off a 2. So if you don't like the 1 primes, you can go back and change all the 1 primes to 1s, so you're back to having only 1s. That keeps it clean, but it isn't really that a big deal. And then you go and prime the first 2. And what that then does is you go back to, you then, for every 1, so you have a bunch of 1s here. Remember, you don't really know how many there are. The Turing machine doesn't know anything about that. But what we can do is we can mark off as many zeros as we have 1s. So we prime these now. So there is the same number of zeros as we have 1s. And then we go back and take the next 2 and prime it. And we're going to mark off again, and probably while we do that, when we do that marking off, we probably change the 1s to 1 primes, so we have to go back and make them 1s again. But that's not really that important. And then we mark off the next zeros, as many as we have 1s. And so what we do then is we do that process for every 2 that we have. And once we've finished with the last 2, primed it, and marked off the last bunch of zeros, presumably the last, that's of course what we have to check. If something goes wrong in that marking off process, if we don't have enough zeros, then obviously this fails. And if we don't have any 1s left, but we still have zeros left, then that fails. But if in the end we have now only 0 primes and only 1 primes and 2 primes, and then there's the blank, then we have verified that this word is in this language. Does that give you an idea how you go about that?
Yes, that does. Thank you.
So the basic idea is you can take a bunch of things and compare it to the same number of things. And in this case, I is equal to j squared simply means that you have everything. You have a bunch of 1s, and you have to do the marking off of those 1s exactly as many times as you do have 1s altogether. So in this case, I use 2 just to keep it clean. You can have different ways of marking if you don't want to get the 2s. So you have a 1 bar and a 1 prime and a 1 bar prime and something like that. So you can get rid of the 2 if that bothers you. But this is probably the cleanest way to go about that. Any questions about that?
No, that makes sense. Thank you.
Okay. Any other questions?
I have a quick question about on the exercise set. The first set of questions, so question 1D.
Yes.
I'm having trouble sort of constructing a word, you know, for that example, sort of kind of having trouble understanding how to like develop the pumping link for that specific question. Like I've understood at this point, you know, how to examine each cases, but I think the early part in that specific problem I'm having trouble with.
So this is 0, I, 1j, 2k, and then this kind of tricky thing is I greater than 2j greater than 3k, and that is greater or equal to 1. Now this is a little tricky, and obviously I don't plan on bringing this kind of question in the exam, because you really have to spend quite a bit of time figuring this out. But basically, the best way is to take, say, I is equal to 2j equal to 3k. So that means you take a quantum m and you make k, well, you put the I is equal to 2k, and it is equal to 2j and 3k. So essentially, you're looking at j is equal to 3m, and k is equal to 2m. So what you have then is that I is equal to 6m. And then, so what you have then from this is 6m is equal to 2 times 3m is equal to 3 times 2m. Okay, so that is correct. And then you simply have to, because these are not equal, greater or equal, these are strictly greater, so you actually have to make you can say that we have 6m plus 2 greater to 2 times 3m plus 1 greater to 3 times 2m. So the m then is some arbitrary value. In fact, the m can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And for each value of m, you're going to get a word that satisfies this, so that's in there. So if you then take capital N to be the value in the pumping lemma, the constant in the pumping lemma, if you take m is equal to capital N, then obviously you're going to get a word that satisfies everything, and that's sort of the closest to the edge as you can, because here we put equal, and then we do this so that we get as close to the equality with those inequalities as we can. So the I equal to 2j equal to 3k, this is putting the equality here, and then by adding 1 here to the 2j and 2 here to the I is going to give you precisely a word that is as close to equality, satisfying those inequalities as it can be. And then by taking that quantity little m to be the capital N, which is the constant of the pumping lemma, gives you then a word that is long enough that satisfies all the requirements of the pumping lemma, and then you can do the pumping. Does that?
Yes, that was very helpful. I was very, very close. On the right side of the right inequality, I did multiply by 2. So I had 3m instead of 3 times 2m, and that was making it pretty much impossible. So this was
Right,
very helpful.
right. That's why you have to go with a 6.
Yeah, okay, thank you. This clears it up perfectly.
Yeah, as I said, this is a tricky one, and that's not what I'm going to plan to have on the exam. But it certainly gives you a little bit of insight of all the things that can be done. Any other questions?
I have a question on building the language for the NP for, I think this is actually in the exercise set number 2B.
2B.
Yeah, this is a construct the PDAP.
Exercise set which number? Exercise set 3 or exercise set 2?
Exercise set 3.
3, okay. Oh, and you want question what? 2B?
Yes, 2B. So I understand once I can get once it's in the 2A form, I can actually do it from there. But whenever I'm seeing it from here in the 2B form, I need to be able to extract the actual formula from there, and that's always a little bit hard, and I do not have enough references. So I wanted to see if we could
All right, let's look at 2B. So the grammar is S goes to A S D or A A D, and then we have A goes to B A C or B C. So that's actually not very complicated, because if you look at that from the S, you can basically generate matching ADs, as many as you want. Think of the A as a opening parenthesis and the D as a closing parenthesis. You now have matched pairs nested. And eventually you will have to go with the S goes to little a, capital AD. And so if you just look at the capital A production, well, what are you going to get? You get a bunch of B's followed by the same number of C's, and they have to be at least one. I'm sorry, you need at least one of these, because go from capital A to BC, that'll give you one B and one C. If you go A to BAC, then you get at least one more matching B's and C's, so this is I greater or equal to 1. And then you have the A's from ADs, correspond the pairing of A's and D's, so this is A to the J, followed by AD to the J. That's basically doing this first production as many times as you want, and then you have to use the S goes to AAD production. And so this is again J greater or equal to 1, because you have to do, you may not use this one at all, but you do have to use this one, which is going to give you one A and one D with the capital A sitting in the middle. So what you're going to get is A to the J, B to the I, C to the I, D to the J, and I and J are both greater or equal to 1. They're, of course, independent. Okay? And so what you have to do then is you read a word, you put a marker for every A that you see. There's at least one A, so you don't have to worry about the epsilon in this particular case. So you put a marker for every little a on the stack. Say you put A's on for every capital A for every little a, and you keep on doing that as long as you see little a's, and eventually you're going to see little b's, in which case you're going to, so you have a bunch of a's on the stack. Say there's your bottom marker, and so that basically gives you however many little a's you've seen, because you put a marker on the stack for every little a that you've seen. Then once you go to b's, then, and that means you have to now switch to another state, so you then go to putting b markers on top of the stack, and so that keeps on going until you actually see the first little c. And for every little c that you see, you take a b marker off. And so that matches the number of c's with the number of little c's with the number of little b's that you've seen. So you take off all those b markers off. For every little c that you see, you take a b marker off, and then presumably then you see a little d. For every little d, you take an a marker off, and at some point, if everything matches up, so if the a's, the number of little a's matches up with the little d's, or more correctly, the number of d's matches up with the little a's, then you expose the bottom marker, the z of the stack, and at that point then you can go into final state or empty the stack. In either case, you have this language. Okay?
Professor?
Yes.
Since this is in the Grayback normal form, can we construct a PDF with
What is in Grayback normal form?
the language given? Can we convert
No,
into
not
Grayback
quite.
normal form and do it by PDF with which accepts the empty
You
stack?
can do that. You can do that. That's certainly a possibility. You have to replace the little d by xd and the little c by xc, so that converts it to Grayback normal form. And in that case, you have a push-down automaton that accepts by empty stack. You then would have to convert that into one that accepts by final state.
Yeah, that would be quite easy than this, all right?
Yeah, but I mean, it's not that hard to do it the way I explained. But yes, certainly what you're proposing is certainly correct as well.
Thank you, Professor.
Sure. Any other questions?
Yeah, I have a question for in exercise set 3, number 2. At the bottom, it has Roman numeral 1 and 2 saying L equals LP, and then the other one L equals NP. What is that referring to?
We talked about that extensively in class. The first one is accepting by final state, L of P, and the second one is accepting by empty stack, N of P.
Okay. So you need to do that for all of them?
Yes.
Okay.
But of course, in some cases you can construct things in a way that will accept by both final state and empty stack, in which case you have basically one push-down automaton which satisfies both questions. But so what I just explained here, you can do that obviously so that the same push-down automaton accepts by final state and by empty stack. On the other hand, if you take the question 2b and convert it into Greiborg normal form grammar, which is quite simple, and then apply the construction that we talked about in class, the one that gives you a push-down automaton with a single state, then that gives you only a push-down automaton that accepts by empty stack. It will not accept by final state, and so in order to accept by final state, you then would have to convert that to a push-down automaton that does in fact accept by final state. That would require adding an additional bottom marker for the stack and a new initial state, so that the conversion of a new initial state, so that you can convert properly to a final state when the push-down automaton, the original push-down automaton, would empty its stack, because obviously if the stack is empty, then you can't continue doing anything, because there's nothing that allows you to keep on moving, so you need something that allows you to keep on moving. But other than that, basically it says you are supposed to give for each of those four languages a push-down automaton that accepts by final state, L of P, and another push-down automaton that accepts by empty stack. That is the second question. But of course, as I said, in many cases you can do that with the same push-down automaton. Does that clarify it?
Yes, sir.
Okay.
Professor, wait, I want to follow up on that because I think you said something very important, but I want to make sure that I know that I'm writing it down correctly. The difference between an acceptance by final state as well as an acceptance by stack is that the acceptance by final state actually includes empty in another.
No, it doesn't. No. You have to the acceptance by final state is acceptance by final state. You end up in a final state if you've consumed the entire input, and you end up in a final state, then that input is accepted. If you accept by empty stack, then that basically means you consume all the input and you end up with an empty stack, which of course means you can't continue moving, because once the stack is empty, you're no longer capable of continue to move. But if the stack is empty and, as I said, you've consumed all your input, then that input is accepted. Does that clarify it? Hello?
Yes. So does that mean that if I put like at the stack symbol, I put a empty state there, that'll actually accept by.
Well, what is an empty state? I don't know what an empty state is.
I'm sorry. So like, if I put like an empty at where, like, let's just say I have Q1 and Q0, and in Q1 in the empty side, I put the Q1 leads to empty. Does that actually clear out the stack?
Oh, you mean that Q sub E that clears out the stack? Yeah, if it removes a stack symbol, then and it does it for every stack symbol that is there, and it consumes epsilon, which means it doesn't consume anything of the input, then if all the input is already consumed, and you then transition from a final state to that Q sub E using an epsilon transition, and in Q sub E you clear out everything, including the new initial stack symbol, then yes, it will clear out the stack, and you will have now acceptance by empty stack. Okay?
Yes, I think I understand it.
Any other questions?
Professor, for this example, could you please show how do we convert from acceptance by empty stack to acceptance by final state?
Well, that's the construction we talked about extensively in class. So, basically you have this is where you have your stack. So this is the stack of the original push-down automaton. So this is your P, and it accepts by empty stack. And now you want to have one that accepts by final state. So you have to basically simulate the P, this one, by putting a Z0 prime. So this is a new stack symbol, new initial stack symbol. New meaning that it doesn't exist in P. And then once the stack is empty, which is of course signaled by Z sub 0 prime being on top of the stack, at that point then you have your, say, Q sub F, and so we have A and B and C, and there may be stuff in all of them. Finally, for epsilon, we go to Q E, and clearing this out. Now this is, well, I should be more specific. There are stack symbols, so we have Z0 prime and Z0, and then A and B and so on. And so this one clearly will have nothing for any of the original letters, because Z0 prime isn't known in P. So there's stuff here for the other stack symbols, Z0 and A and B and whatever else. And so in QF, that's only for a final state, we then, when we see the Z0 prime exposed on top of the stack, which of course signals essentially that the old push-down automaton P emptied its stack, okay? At that point, we consume epsilon and go to QE, and we remove the Z0 prime, and that then guarantees that we have, I'm sorry, what am I doing? I'm doing empty, I'm sorry, this is F, final state. We have a, is that your question? You have a automaton, push-down automaton that accepts by empty stack, and you want one that accepts by final state. Is that what you're asking?
Yes, Professor.
Okay, all right. So, yes, I'm confused, was a little bit confused. So at that point, the only, so this is not QF, this is any state. So this is in the old, this is in P. Okay, any state that where the new initial stack symbol is exposed. At that point, we then read epsilon from the input, meaning that there's nothing to be consumed, and we then transition from whatever state we have. This is for all Q's, every single one of them in P. We transition to that final state and we stop then. Is that clarified?
Professor, does that mean that we just have to add a new stack symbol and a final state?
No, it's a little bit more complicated than that. You also need, if you remember, we need a new initial state, because basically what we need to do is for that new initial stack symbol and that new initial state under not consume, we consume epsilon, we go from there to Q0, the initial state of the push-down automaton, and we put Z0, the initial state of the push-down automaton P, by Z0 prime. So everything is nothing else. And for all the other stack symbols, this is nothing. So this basically just allows us to go into P. So we're in P prime. In P prime, we have Q0 prime as initial state. We have Z0 prime as the initial stack symbol. And so we now transition into Q0, the initial state of P, and we put Z0 on top of the Z0 prime. So that then guarantees that whenever the P, the push-down automaton that accepts by empty stack, clears out its stack, it means that that is precisely signaled when Z0 prime is exposed on top of the stack. And at that point, and that holds for every state, whenever the Z0 prime is exposed on top of the stack, we transition to that final state QF. So you need a Q0 prime, a QF, and you need a new Z0 prime. Okay?
Yeah. Thank you, Professor.
Any other questions? Any other questions? No other questions? Well, in that case, let's see. What I'm going to do now is essentially in preparation. It's not going to be on the exam, but it is in preparation for what we're going to continue doing with Turing machines, except it gives you a bit of a feeling, maybe an uneasy feeling, but still a feeling of the kinds of things that we're going to be interested in starting next Monday. And basically what we're going to look at is the halting problem for Turing machines. Now, we never had a problem that we could consider complicated with the automata that we were dealing with when it came to the question, does this thing halt? Does it stop? Does it say, yeah, accepted, no, not accepted? With Turing machines, it certainly isn't entirely obvious how you can be certain that the Turing machine halts. Obviously, we can clearly construct a Turing machine that will not halt. I mean, I can construct a Turing machine that basically takes the input, whatever input there is, and then goes beyond the end of the input and takes that first blank and changes into a 0, and then continues to the right and takes the next blank and changes it to a 0, and keeps on doing it. Obviously, this Turing machine will not halt because it will always encounter another blank to the right of the 0 that it's just written, and so it will clearly not terminate. Now, in this particular case, it is, of course, fairly trivial to conclude, yes, this sucker is not going to terminate. Whether this makes sense or not is a separate issue. In this particular case, this is simply an example that gives you a clear and very trivial illustration that Turing machines need not terminate, can go on forever. But the fundamental problem that we're going to have to grapple with is, can we determine whether a Turing machine will halt for some input? So now we're no longer looking at the question, given a specific instance of an input and a Turing machine, will that Turing machine halt? Now we're looking at, well, can I come up with an algorithm, a process that will take a Turing machine and an input and say, yes, this Turing machine will halt, or no, this Turing machine will not halt. And that's the kind of thing that looks quite esoteric, but can be rather profound. Because what we're going to see is that we cannot do that. We cannot take a Turing machine and an input, and we have yes, it halts, or no, it doesn't halt, as output of this algorithm that would solve the problem whether a Turing machine will halt for some input. Now, when we encounter this kind of problem, this is called undecidability. So a problem is undecidable if there does not exist an algorithm to resolve it. And the standard example that one considers in this context, standard example of an undecidable problem, is the halting problem for Turing machines. Given a Turing machine and an input, does that Turing machine halt on that input? Yes or no? Can't be done. Does not exist. So you may say, all right, who cares about Turing machines? Who cares about whether they halt? Well, let me give you an example that is perhaps far more intuitive than the question of the halting problem for Turing machines, which is the post-correspondence problem. PCP. Emil Post was a Norwegian mathematician about 100 years ago or so. And it turns out to be a deceptively simple problem. Here is what we have. We have strings W1 through WK and X1 through XK. So we'll have two lists, call it A and call it B. The only thing we stipulate is that they have the same number of elements, even though that is not that particularly important. So the WI's and the XI's are all from over a certain alphabet. We do not permit empty strings, so we stipulate that they be all at least of length 1. And so that's what we're given. And then the post-correspondence problem has a solution if and only if there exists I1 through IM for some m greater or equal to 1, such that WI1 concatenated with WI2 concatenated, etc., with WIM is equal to XI1 concatenated with XI2 concatenated with XIM. So this looks like a fairly trivial kind of problem. And so let's look at a simple example. Suppose we have, yes?
I don't understand the problem. Could you explain it one more time? I'm writing it down as well, so that actually might slow me down. But I wanted to.
I'll give you an example that will clarify it. So let's say we have, this is your I, we have 3, K is 3, okay? And list A is 1 and 1 0 1 1 1 and 1 0. So these are the three elements in the list A. And then we have the list B, which is this, and we have 3 1s and 1 0 and 0. And so in this case, W1 is 1, W2 is 1 0 1 1 1, and W3 is 1 0. And X1 is 1 1 1, and X2 is 1 0, and X3 is 0. And so the question is, can you find indices I1 through IM for some M such that when you concatenate the corresponding words from list A with those indices, that is exactly equal to the corresponding list with the same indices from words with the same indices taken from list B. So in this case, I claim that there exists a solution. M is 4, and say I1 is 2, I2 is 1, I3 is 1, and I4 is 3. So if I take the W2, W1, W1, W3, then I get W2 is 1 0 1 1 1, W1 is 1, W3 is 1, and W4 is 1 0. So if I put dots there to just delineate the end of the various words, that's of course not really important. And now I look at the x's. So x, the first word is x2, so this is 1 0. Then I2 is 1, so that's 3 1s. I3 is 1. That's another 3 zeros, 3 1s. And 3 is 1 0. I4 is 3, which is 1 0. So we have 2, which is ends here. And then I2 is 1, which is 3 1s. Another 3 1s, and then this. And so if you now look at this, then obviously these match up. These are exactly the same. So this has a solution. Does that clarify it?
I think on the bottom you have one extra one.
No. I have 3 1s, 1 0, 3 1s, 3 1s, and 1 0.
I think there's more ones on the one on the bottom than the top.
Right. Let me see what did I screw up.
I think for I4, 3, you used the 1 in A, 1 0 instead of B, which is just 0.
Oh, yep. Okay. Sorry about that. I used 2 rather than 3. So that means I have that. Correct. Sorry. So, yes. Okay. Right. Let's verify it again. So for the x's, we have 2, which is 1 0, 1 0, and then twice the first one, which is 3 ones, and then 3, which is a 0. Okay, and so that matches up. So this is the same. This. Yeah, sorry. Okay. So in this particular case, this instance of the post-correspondence problem has a solution because there exist indices, in this case, 4, I1, I2, I3, I4, so that I can, if I grab the corresponding strings with the appropriate indices from list A, and I grab the corresponding strings with the same indices from list B, I'm going to get exactly the same string, which is what this says. So the post-correspondence problem then is the input are 2 lists, and the output is supposed to be yes, there is a solution, or no, there isn't. Now, showing that things don't have a solution can be a little trickier. Let me give you an example of that as well. Again, we have 3 strings, and list A is 1 0 and 0 1 1 and 1 0 1, and list B is 1 0 1 and 1 1 and 0 1 1. And so obviously looking at this, so this is list A, this is list B, it follows that there is no way you can start your I1 with 2 or 3, because for 2, the word from list A starts with 0, and the word for list B starts with 1. And similarly, if I1 is 3, you have again a clash. So it follows that if there is a solution, I1 has to be 1. So we have 1 0, and we have 1 0 1. So now we need a 1, and that 1 has to be 1 0, because, well, if it were 1 0, then there is no, well, what it basically boils down to is, so if this would be, if you have that, so you have 1 0 from the A list, and you have 1 0 from the B list, and so you then need something that is a 1 here for the A, and there are 2 possibilities. You can have either 1 0 or 1 0 1, and in the case of the first one, for B, you need a 0, which is 0 1 1, and for the second one, you need well, you need the same thing, but you can easily verify that this does not terminate. So you will find indices I2 and I3 and so on, but it will never end. So in this case, you can work out that this does not terminate and therefore does not have a solution. However, the problem is that this is the general question. This general question basically says, given arbitrary lists A and B, can we say, yes, it has a solution, or no, it does not? And that turns out to be impossible. This cannot exist. So what that means then is that basically we are confronted now with the question, or the problem, that there are problems that we can formulate for which there does not exist an algorithm that will solve the problem. So that kind of question is philosophically uncomfortable, because it basically goes against our expectations. We tend to think that if we just work hard enough and plug away, we will be able to solve the problem. And that's not really necessarily true. The post-correspondence problem cannot be solved. The halting problem for Turing machines, which seems to be more esoteric, but still it is very similar in a way to the post-correspondence problem, does not have a solution. So given two lists, do there exist indices such that the corresponding words from each list are equal? We don't know. We cannot solve that in general. Now, as you can see from these examples, this example does have a solution. This example does not have a solution. So in particular instances, for specific A's and B's, you can typically reach an answer yes or no. But the fundamental problem that we're dealing with here is that we will never be able to design an algorithm, if you will, a black box that takes two lists, A and B, as inputs and answers yay or nay. That is impossible. That cannot be done. And this isn't a question of being lazy or being stupid or inept or incompetent. This is not going to be, the answer to that question is not going to be different in a year, in 100 years, in 1,000,000 years. No amount of intelligence is going to allow us to solve an undecidable problem.
Professor,
Yes.
why does this this kind of the Turing machine halting problem comes up a lot whenever we're talking about artificial intelligence? Is the number one time whenever I hear about Turing and almost anything he has done usually has something to do in that regard, even though I kind of understand that he was a mathematician overall.
And so Turing machines are basically a mathematical object. You wouldn't want to use a Turing machine to solve anything. It's basically a formalism that allows you to talk about what can be done, or in this particular case, what cannot be done. And it is important because there are problems that one can run into quite easily that are deceptively simple, like matching up these words from two lists. And yet, if somebody wanted to come up with an algorithm to do that, that would be a completely futile undertaking because it can't be done.
So in artificial intelligence, what they're actually saying is that no computer would actually be able to do this. So it don't even try
If
doing it.
you can show that something is undecidable, then you have to be a moron trying to solve it. Because it will not work. You will never be able to solve it if it is undecidable. Now, if you have a specific instance, yes. But if you want a general solution to that problem that you've already determined to be undecidable, then it is completely moronic to try to do that because it will never, you may as well just take money and burn it. Because it can't be done. And as I said, this isn't a question of, well, if we wait another 100 years and we have a lot more compute power and we're much more intelligent. No, has nothing to do with that, has nothing to do with intelligence, has nothing to do with compute power. It is a question of, can it be done? And we can prove mathematically that it cannot be done. That's basically the fundamental challenge, the fundamental philosophical problem that we tend to have. Our expectation usually is that, well, if we just work hard enough, we'll be able to solve that. That usually is the case, but if you know a problem is undecidable, then there is absolutely nothing that you can do about it. No amount of hard work is going to solve that. I usually make sort of a little bit fun of that. This is the ultimate un-American problem because the usual can-do approach of Americans is, well, if we just work hard enough, we can solve it. Well, unfortunately, if it's undecidable, no amount of hard work is going to get you anywhere. Any questions about this? So we'll deal with the halting problem for Turing machines. Where are we? Here, there. Formally, the post-correspondence problem typically is shown to be undecidable by reducing it to the halting problem. So the halting problem is really what people typically use for undecidability issues. And that's what we're going to do. It will be somewhat esoteric, but I want to make sure that you understand that there's nothing esoteric about undecidability, because if you try to solve an undecidable problem, you are simply throwing money out of the window, because it's not going to get you anywhere.
I have a question.
Yes?
Are problems undecidable because they extend forever?
No. No. if you look at, well, I guess you think that this problem, if you sort of work it out, suggests that it will just not finish. That's really not necessarily the case. Let me give you an example. If I have two context-free grammars, it is a reasonable question to ask whether those two context-free grammars generate the same language. The example might be E goes to E plus T, or T and T goes to T times F, or F and F goes to open paren, E close paren, or ID. And the other one would be E goes to E plus T. I'm sorry, E plus E. E goes to E times E, open E, closed E, and ID. Now this is the evil, ambiguous grammar, but the language that is generated by this grammar, you can easily see is exactly the same as that. So in this particular case, we can immediately say, yes, the answer is yes, these two generate exactly the same language. Unfortunately, this is undecidable in general. So if I give you two arbitrary context-free grammars, and I ask you to come up with an algorithm that determines whether those two grammars generate the same language, I basically have to really hate you, because I'm asking you to do something that is impossible. I wouldn't do that. But that's the kind of practical aspect if you were to want to determine whether two context-free grammars generate the same language. Well, that would be a very foolish thing to try to do, because it is well known to be undecidable. So it really has not that much to do with things going indefinitely. The point here is that certain questions simply can't be answered in general. Does that sort of make it easier to see? Whoever asked that question.
Yes, that made sense. Thanks.
Any other questions?
I actually have a quick question.
You have to speak up. I don't hear anything.
I have a question I meant to ask at the beginning of class, but is sort of relevant again. In this example, you put ID at the end of the productions, and there's a similar problem in the exercise set, and you've used this in class before. I am sort of confused on what that term means, because it seems like it when you used it in an example, it kind of generated terminals that like
Right.
A, B, or
Well,
C.
ID is just, I mean, if you want, say, ID plus ID times ID, that's what it would generate. What I typically do is A plus B times C. So each A, B, and C is an instance of ID, and that way it's clear. You identify A, B, and C with ID. That's all it is.
Oh, okay. They're just sort of unique instances.
Don't overthink it.
Okay.
It's as simple as that.
Thank you.
Sure. Any other questions?
Could you go back to slide 3, please?
Sure. You want me to go through all the slides?
Yeah, that'd be great.
Okay, sure, no problem. Slide 1. Slide 2. Slide 3. Slide 4. And slide 5.
Thank you.
Sure. Anything else?
Is the exam going to be open at 2, like last time?
Yeah, I have never given a closed book exam. I have no use for closed book exams.
I think he said open at 2, like as in.
Oh, open at 2. Yes, yes. We'll just continue the way we've been doing it last time. That seems to have worked. Okay. Anything else? All right. Good luck on Wednesday. Bye-bye.